So in the experiments, first you have some sample and you have some loading system. You paint some pattern. So usually it's a random speckle pattern on the top surface of the sample. So you use a high-speed camera to record the images during the deformation. So you have some video like this, and you have the image sequence. And then you apply some image tracking algorithm. You can solve what's the displacement field, like what's the X displacement, Y displacement. And from the displacements, you also know what's the strain field. So that's a typical 2D digital image correlation. If the top surface is not planar, it is some curved top surface, so you need more than one camera. So that's the 3D stereo digital image correlation. So where you can measure the out of plane deformation. So besides this 2D, 3D, there are also many images. They are volumetric. Like many of those images in Frank Lab and in Always Lab, you have those volumetric. Volumetric means these images are not only two-dimensional, they are three-dimensional. So besides the X dimension and the Y dimension, you also scan the images in the Z stacks. So finally, you have some images, it looks like three-dimensional. So again, same as before, you have some reference undeformed image. You have some default image. You apply some image tracking algorithm. You can get the displacement field and get the strain field. So all these called the digital image and the volume correlation because they use the digital images and you do some correlation to perform the image trackings. Okay, so why they are useful? Because you can see there are lots of the experimental techniques can give you the full field definition. So for example, imagine you are loading some sample. So now you measure the deformation, the strain. So if you also know the stress, right? So you can characterize the material's properties. And because you have high-speed camera, you can measure those stress-strain relation at the different strain rates, right? So imagine this is just a linear one-dimensional spring. So you can measure that stiffness or Young's modulus for that spring. So actually, the model can be more complex and the whole 3D models. And to take these images, there are many methods, right? So you can use the very classic, even use your iPhone, you can take some images before and after deformation. But if you can use some other diagnostic tools, like for example, the atomic force microscopy or confocal microscopy, some scanning electron microscopy, or like some camera or satellite images, you can capture a wide range of those deformations from the nanometer to kilometers. So it's a very general experimental method and give you very complex full field deformation and quite easy to use. So that's why nowadays it's very popular. And besides this, solid materials, in fluid mechanics, people use a similar method called PIV, particle image velocimeter. But the idea is similar. You capture some images and you do some image tracking algorithm and you measure the deformations. So previously, what I showed you is for the 2D applications. So for digital volume correlation, you can imagine. So now you have the three-dimensional images, right? So you can measure the 3D deformations. Yeah. So for example, you can use the X-ray CT scan to measure what happened inside the materials. Like if there's the granular mechanics, you can measure those heterogeneous force chain. Or like for the cell mechanics, you can measure what's the interaction force between the cell and the surrounding substrates or surrounding materials. So that's the lots of the DVC applications of tool to solve those three-dimensional volumetric deformations. So even after today, you can always check this. There's the International Digital Image Correlation Society. There are lots of the open source codes and the resources there. So for example, if you go to this link, I will share these slides after this meeting. So for example, in the guide, there's a very nice detailed book to give you lots of the guide, how do you design and conduct your experiments. And in the resources section, there are also lots of the commercial codes and the research codes there. Yeah, our codes are also listed there. Also, there are many codes have a GUI tools you can easily apply, or some MATLAB or Python codes you can easily combine with your own research. So besides the IDIC website, right? So I would recommend the one book written by Michael Sutton and Hubert Sherwood. Michael Sutton is one of those pioneers in this field. There's a very nice book there. There are also lots of the resources in Kinematic downloads page, and also my own website. There's lots of the codes and the demo videos there. Yeah, feel free to check them. Okay, so that's the introduction for the DIC DVC. So there's some. So before we started the section 2, is there any question there for the first part? If you have a question, just feel free to speak out. Okay, so if you know, we'll go to the second question. So what's the practical guide for your DIC and DVC experiments? So first, I will introduce what's the guide for the 2D DIC experiments. So as I said before, because it's a digital image correlation, right? So you need some digital images. You need some camera to capture those images because there's a correlation. So you need some software to do the correlation to track the images. Right? And also the image quality, it depends on the accuracy depends on the image quality. Image quality also depends on your experiment setup. So all they basically have the 4 parts you need to pay attention. That's the loading system, will give you definition, and that's the patterns. How do you paint the speckle pattern on the top of the surface, and how do you image them, and how do you do the post-processing to solve those definitions. So for the loading part, here's one of those examples. This is typical what the DIC experiment setup is. You have some sample there onto the definition, and then you have some specimen painted with the pattern, and you have some light source to to give the loss of the lighting, and you have the high-speed camera to take the images. And after all these images, you put them into some software or code to solve the definitions. So for the loading system, one thing you need to pay attention is you cannot distort those images with lots of those very bad definition, like a distortion or misalignment. Or if you marry the 2D definition, you need to make sure your definition is always on the plane. Otherwise, you need to have the stereo to 3D DIC. Also, your images cannot have much of this vibration or noise, right? Because those images can be blurred, so it will affect the accuracy for the image tracking afterwards. So just pay attention to this. Basically, what you want is you have some reference image, and after those loading, you have some deformed image. This deformed image looks nice, not blurred, and the change of the image just to affect what the real definition is. So that's you are good with this loading system setup. So besides the loading, you also need to print some pattern on the top surface. Why you need a pattern is because you need a pattern to track the image definition. If there's nothing there, there's no way you can track them. So pattern needs some pattern quality because the bad pattern quality will give you bad correlation results, which means you have bad displacement in stream field. So you need some good quality. So I will tell you what means a bad pattern, good pattern. So bad pattern usually means these features can be quite sparse, which means this, you can see there are just much less of those dots compared to good pattern. So bad pattern, you have more features there. So it will give you much more better accurate results. So for those pattern technique, there are many methods you do. You can use some airbrush, you can use some stamps or some roller. Also, you can use some etching method or some 3D printing or inkjet printer. The key idea is to print some of those random speckle patterns. There are more details how do we define a good pattern in the next 2 slides. So here's one of those examples is that you can use those like oil painting or brush or roller or some, just maybe use some fiber, you can paint these patterns. Or you can use some very nice 3D printer or the handheld inkjet printer, right? You can print all the designed patterns on the top surface of the specimen. Like all these printed patterns can be very nice because their pattern can be precisely controlled, and the pattern can be very nicely repeated. Also, the track definition is more accurate. So this is typical what the pattern looks like. Basically, what you want is you want the entire top surface of the sample have the random, very nice those black or white dots, or some, they may not be dots, but some part have white, some part have black, and they are random. And for each one of those typical feature or dot, for example, Q1 or Q1 should have the size about 3 to 5 pixels for each of those feature or dot. And later on, when we track this deformation, we will define something called a subset, because we track the local window deformation, and this window will have about 3 to 8 of those dots. And also this area, right, you need to guarantee there is a very nice high contrast, and also 50% white, 50% black give you best results. But this is not some absolute values. The key idea is that you have enough features, you can track them afterwards. Also, some people may ask, can I just use the larger speckle dots? You can, but you may lose some spatial resolution afterwards, just to pay attention to those. Basically, all these dots size, right? For this length scale, you need to satisfy the Shannon sampling frequency, right? So it means like you should have some estimate for your deformation characteristic length, and then you can define what's the typical dot size for your patterns. Right? Yeah, just one final message is for each of those dots, the typical size is 3 to 5 pixels, and roughly for this whole area is 50% white, 50% black, and all the pattern should look like a random, non-repeatable, and they can be dot or they can be connected, but they should be random. So besides the loading and the pattern, and the next is for the image system and for the lighting. So you may need some additional lighting panel to light on your top surface of specimen. You should not to let some shadow or some blur to affect the DIC experiments. Also for your painting ink, right? They should not be reflective. They should not like they have different angle or different area. They reflect different lights. That will change the image quality as well. Also for your camera, they should not be set up with some image stabilization or autofocus. You should not use the compressed image formats. So all that needed is you want to let the camera is just to camera what the light resource or phonons it captured. You should not to let the camera have some additional adjustment or some calibration to change those image patterns. So that will not affect what the real deformation for the specimen. Okay, so after all this, like you have the loading, you have the pattern, you have the imaging, you have the light source, and then you have the image sequence, and then you have the source software or code to do the post-processing. So I will talk about this algorithm in the next section. So besides the DIC, I will talk a little more about the DVC environments. So DVC is very similar with the DIC. The only most difference is how to capture those images, right? Because the DVC you need some volumetric images, right? So you may need to scan those Z stacks for the volumetric images. So first, similarly for each of those pattern or dot or size, it should have the diameter still around 3 to 5 voxels. That's the same. And finally, for the typical for the post-processing, we always have those box, and we measure those box deformation. And this box will have the size about 10 power 3. Power 3 because it's in the volumetric in the 3 dimension to 30 power 3 voxels. So which means for those DVC measurements, typically you need some more Z stacks. And also for the bit density, you should similarly have some almost like 50% of white or 50% of black. Again, this is not the absolute value, right? Just make sure you have enough features you can track afterwards. So here's one of the example is if you have those 0.03 beats per voxel for the beat density, you have a nice those patterns for the DBC experiments. Here's another this is from the real experimental data set from the Georgia Tech and Emory University. So they only have the Z stacks like 78 voxels, and then their X and Y is 500. So even the Z number is much smaller than the X and the Y, the voxel numbers, right? But at the end, you can have several tens, which means you can finally, you have lots of the box you can track, that's good. But if you have just, for example, 3 or 5 voxels, they may give you lots of the trouble to apply DVC deformations. There are some other methods, like a particle tracking or some other method we'll introduce tomorrow. But it's really typical for the DVC. You need a kind of some volumetric images, right? And imagine those volumetric size. You need to have some certain number, usually tens of those in the Z direction. X1 usually is okay. Lots of those cameras, it's okay to have lots of X and Y for the voxel numbers. So there's some question for this part for the section 2. The question? Okay, if there's no question, we'll go to the third part. So now we have those images, right? So how do we perform the post-processing to track the image deformation? And after this section, I will show you the codes. Because of the time limit, today I will just cover some of those topics, the local method and AR method. So lots of those advanced topics, they're the open source code I will provide, but I will not cover them today. So for the local method, so before we introduce these methods, we need to just define what the problem we are solving. So images, actually there. So if you put in the MATLAB or other codes, they are actually just as a matrix. So for the 2D images, the grayscale value for the image, that's some scalar function with the coordinates. And absolutely because you have digital image, so all this is the discrete matrix. And for the deformed image, you have another matrix, right? So you know the grayscale value for the reference image fx, and you know the deformed image who the grayscale value is the gy. So you know fx and you know gy, and you make the assumption that fx transform go to the gy exactly to review what's the deformation of the sample, right? And so you want to solve the mapping from x to y. So you can solve this by minimizing the summation of the squared difference correlation function. So where to minimize the sum of the f minus g and the squared and the sum of the minimum over y. Equivalently, you can also maximize the cross correlation function. So where it's not the f minus g squared again, it's f times g. So they are equivalent. So for example, if you expand the SSD correlation function, right? So f minus g squared equal to f squared plus g squared and minus 2f times g, right? Because for those speckle patterns, the f squared and the g squared, they're almost constant. So you can see minimize minus 2 times f times g will equivalent to you maximize the f times g, right? So that's why these two correlation functions, they are equivalent. So besides these two correlation functions, there are also many other correlation functions used. The two popular ones, the zero normalized SSD and the zero normalized cross correlation. So the only difference is there is some zero normalized. Zero normalized means you put the f and the g, so you minus the mean value, and then you divide the standard deviation. So here's the question for the audience. So can you imagine like what's the benefits we do the zero normalization compared with the we didn't do those? If you have some thoughts, just feel free to share.
You can minimize the effect of changing your optical system, like lightning, right?
Yeah, that's great. Yeah, that's good. A very good point. Yeah, thanks. Yeah, so just like imagine so if your f and g if everything is the ideal setup, right? So F exactly goes to G. So this you can see the non-zero normalized should have the same results with the zero normalized, right? But because there we can have some experimental noise or some lightning change or something. So F and G, they may not ideally equal, right? So they may have some, you can see linear distortion or something like that, right? So if you still apply the non-zero normalized, you may have some error there. But all this like linear distortion still give you very good results if you apply the zero normalization. So actually, from the theory, they are equivalent. Just in practice, what we applied is the bottom two state-of-art zero normalized correlation functions. Yeah, but for the analysis, it's the same. Okay, so so first I will introduce the local method. Local method is even though there's a big image, right? But what we do is we cut this big image for many local subsets, and we assume, for example, the simplest assumption is each subset has a rigid body translation. So, for example, each of those orange boxes to shift to some other place, and this shifting vector, that's a displacement, right? So then you can see, okay, now the y-axis we have the translation assumption where y-axis equals u plus x, right? U the displacement. So I can choose to maximize the cross correlation function. I can just compute what the cross correlation function looks like, right? If you plot this function with the x u, so u the displacement, because the displacement you have the x displacement, you have the y displacement. So if you plot the cross correlation function with the ux and uy, it will look like this. So their peak value. So this peak value position, that's the exact ux and uy. Also, why we choose the cross correlation function, because this correlation function, you can use the fast Fourier transform. You can very easily to compute. It's super fast. So the question for you afterwards is to prove this cross correlation function, that this identity is correct. You can search Wikipedia if you need the answer. And once you get those cross correlation function, you can use some Gaussian or parabolic or sinc function to fit the subpixel accuracy for the peak of the function where it is. So that's your ux and uy. So here you always make assumption that each orange box, they are just the rigid body translation, which means they don't have any rotation or distortion or some anything else, because these are the ansatz were made. But in the real life, the box can have rotation or distortion, right? Because the sample can be stretched or rotated or sheared, right? So besides the rigid body translation, you can have one order higher assumption. That's the linear fine definition. So now each orange box, so not only have the rigid body translation, the shape for the orange box can also have some rotation, shear, or distortion. So you can see here the y-axis still x plus u, but this u is a linear fine. Linear fine means you have the rigid body translation for the center, and for each box you also have the f, capital F. That's the distortion. That's the gradient of the displacement distortion matrix. And again, you can solve the previous both the minimize SSD correlation or maximize cross correlation. So here another question for the audience. So you can see here the assumption this one is a different compared with the previous one. Right? Because the previous one you only have the u plus x. So now you have the u plus f times x minus x I naught. So I naught is the center for the subset. So can you imagine what's the benefits if we apply this ansatz compared with the rigid translation ansatz? Either any thoughts like so what's the benefits way for this of linear fine assumption? The idea is the key idea is the thing is, so if the subset is just a very nice rigid translation, so these two methods give you same results. The thing is, if your orange box have a very big shear or rotation or like a stretch or distortion, these answers can be very poor. So the accuracy of this method may not work anymore. But for this linear fine deformation, because this assumption include all these possible deformations like rotation or shear or distortion. So this method for the linear fine assumption still gives you good results. So that's the difference between this local method compared with the rigid body transformation. So in a word, if the deformation is small, both of these two methods give you almost the same results. But if your deformation is very large, you have lots of those distortion or rotation or shear, you can only apply the second one, because the previous one had the much larger errors. Again, for this optimization, you can put all the U and F, that's your unknowns for each subset. And you assume U and F is the same constant values for each subset. But the different orange box, they can have different values for U and F. But for each box, you can do the minimization to solve the U and F. If you put a U and F in a long vector, you can apply the Newton-Raphson optimization or inverse composition Gauss-Newton iteration to solve the U and F. Here I'll put the homework on notes. So how to derive this Newton-Raphson scheme. Feel free to ask me a question for this step. The idea is to solve those U and F use some optimization problem. There are many methods there, like not only just the Newton-Raphson or ICG. There's other methods like machine method or a gradient descent or counter gradient descent. But the ICG the best one for during the 14 years. Okay, so that's the local DSM method. Is you cut the whole image domain into many local subsets and you solve each one independently. So there are many. You can see there are many option parameters you need to choose, right? Like how big for your subset it is, right? How dense for their spatial like a distribution, and how do you choose a fine or rigid body or maybe higher order quadratic deformation, right? So all this it depends on the DIC error analysis. So for example, so DIC errors comes from two parts. So for first is each loop subset. If it's too small, you can see the number of the feature included will be small, right? So the answer error will be large. If you have larger subset, you have much better accuracy to measure the uncertainty. So your subset should be not too small. But if your subset is too large, so because you made the assumption, no matter rigid body or linear fine, this assumption may be poor because the definition can be heterogeneous. So there's some discrepancy error for the subsets as well. So the overall the accuracy actually is some U-shaped curve. Either the subset cannot be too small or too large. If the subset is too small, you don't have many features included. If the subset is too large, you may over smooth deformation. So typically the suggestion for each of those subsets is either to include 3 to 8 speckle features or dots inside each of those local subsets. And besides the subset size, so there's another parameter called the subset spacing. So for example, here on the left, there are 4 subsets. Each subset have the same size in the blue arrow line. And between the two neighboring subsets, there's another distance called the subset spacing. Because all these subsets can be solved independently, right? So this subset size and the subset spacing, they can be 2 independent parameters. So if the subset spacing is larger than the subset size, these 4, they don't have any overlapped area. But if the subset spacing is smaller than the subset size, they can have some overlapped region. Right? So typically for the suggestion, they put the subset spacing for 25% or 100% with the subset size. So which means you have some overlapping, but not too much overlapping, usually between 25 to 50 overlapping ratio. Yeah, a very limited case is that you put the subspace in just one pixel. That's the highest spatial resolution you can achieve for the DIC or DVC. Because all these images they are in units of pixel or box. So if we want to achieve the sub-pixel great accuracy, we need to interpret those sub-pixel grayscale value. So just to try to, so here just shares lots of the results in the bicubic or bicubic spline order nice. Higher order or more complex function, they all work, but they may have some additional computational cost. And also for the previous what we introduced is the rigid orange box shift or affine either a translation plus the distortion. You can also add a more complex shape function like a quadratic or some other irregular shape function, right? The typical for the DIC, the affine works very well. Just for general case, right? And most of those DIC, there are lots of the complex error analysis. You can check this paper because they come from the image noise or lots of the experimental setup or interpolation error or like a autoplane motion, lots of those reasons. The good thing is that as long as you don't have much autoplane motion or like some misalignment, the typical error for the DIC is the 0.01 pixel. This is a general idea for the most DIC accuracy. Okay, so besides for now, you just introduce the local DIC method and lots of those like tips you need to take care of when you choose the substrate size and the substrate spacing and the general DIC precision is in the order of the 0.01 pixel. So is there any question for this part? Because data important is so when you deal with your digital images to do the post processing, you will define, user can define what's the subset they use, what the subspaces they choose, right? And also what the shape function they need to choose, and what's the general precision they will achieve. So just give you some idea for this part. No question for this part? Okay. So local method. So next I introduce a more advanced method called the method I developed called Augmented Lagrangian. It's a hybrid local and global method. The difference is in the previous local method, so we know each box is assumed with the rigid body translation U plus the linear fine distortion capital F, right? So and we assume U and F they are independent and each box is independent with other boxes. But we know in a global picture, the capital F, that's the displacement gradient. It should equal to the gradient U because that's definition for the F, capital F. So here we just include this global constraint. This constraint actually is called is global kinematic compatibility constraint. So add this constraint. So now you have some optimization function, but we have some global constraint. And add this global constraint at the Augmented Lagrangian. That's the bottom. So add some penalty terms. So which means I just rewrite this constraint of this problem in the weakening form by using some penalties, and this penalty is in the form of the Augmented Lagrangian. So where I introduce another variable U hat, I want the U hat close to U and the gradient U hat close to F. So we can see add those gradient U. So add two penalties. One penalty is the gradient U hat is close to the F, and another penalty is the U hat close to U. And then I just solve this new optimization problem using the alternating direction method of multiplies. So actually, this ADMM had very nice review paper by Boyd at Stanford. And yeah. So solving this problem, so now you have three variables, U and F and the U hat. So the first step is that you fix the global variable U hat and you solve the U and F. And this U and F, because there's some summation there, so they can be decomposed into many local problems. So they can be solved very fast in parallel and solved locally. And after solving U and F, you can fix the U and F and then solve the U hat. So then because U and F are fixed, the first term is fixed. And solving the second equation, that's just to have some Euler-Lagrange equation, and you have the explicit results. That's the U hat. And also because this problem, the F and the G, they are fixed. So the first term, where there's the grade value, they don't enroll. So you only solve some very nice, simple equation for the U hat. So even though it's a global problem, but because there's no grade values, it can be solved very fast. And then just after do wrap and solve everything iteratively. So a quick summary of this method and compare with other method is the local method. You solve all the subsets. Subsets can be overlapped, but they are all with the solved independent. And each subset is defined with some a fine definition assumption or like a rich body translation assumption. And the global is to solve all the nodes. I don't include it today because of the time limit, but the idea is to solve all the nodes at the same time. And this AR method is you introduce another new U hat. You want the U hat to satisfy the global kinematic problem. And you decompose everything into two sub-problems. First problem is to solve everything locally. And then you just, from the results of the first problem, you solve the global again to guarantee there's the kinematic compatibility. And then you solve iteratively. And it's fast, and you already have a nice compatible results. Just give a quick demo to compare the different methods. Why we have lots of AL, and how do we compare with the global and the local methods? So here, one of those example by my colleague at Caltech is she designed also the 3D printing these materials specimen with the two types of materials. The gray materials is relatively stiff, and the black materials is relatively compliant. And then he made a pre-cut notch, and then it's under a tension fracture test. And then we want to measure what's happening afterwards. So you can see the solved definition, local and global. In this case, the displacement error looks almost the same. But if you look at the string fields, so local is always solved very fast, but because the subsets, they are solved independent, so you lose the global kinematic compatibility. So the substitution may be noisy in the global picture. So global, because you solve everything at the same time, so it's always guaranteed there's the global kinematicity. And the solved solution is always very nice, but they may have more computational cost because you solve all the nodes at the same time. So this method AR gives you best results because it's not only guaranteed there's the kinematic compatibility, and also both the subproblem 1 and the subproblem 2, they all can be solved very fast. So there are some more advanced topics I don't want to show today, but just give you two of those examples. So one example is for the adaptive mesh refinement for the AR-DIC method. So here the example by Ash and Jacob, their lab is for the cell migration problem. So if you try those LDIC, you can apply this with the adaptive mesh. So where the mesh can be adaptively refined to where there are the large definition or high string values. So you can save lots of the potential cost by combining this adaptive mesh strategy. And also another one is not only solve uniform mesh specimen, you can solve very complex geometry. Like here is one of those form under the tension, and there are multiple holes there. So you can apply the adaptive mesh. So here I apply the quadtree adaptive mesh. So you can see all the displaced field and the string fields, they can be very accurately solved. And not only for the continuous case, we also solve lots of those discontinuous case. So here the one example of those mode 1 actual experiments. There are lots of the advanced topics. So because of the time, I don't show today. So DIC and DVC, even though it sounds 1D, 2D, 1D, 3D, but from the algorithm or from the methods part, actually they're almost the same. Just one is the 2-dimensional matrix, one is the 3-dimensional matrix. So DVC have almost the same part with the DIC. So from this point of view. So if there's some question for this part, if not, we'll go to the lots of those hands-on code demos. Is there something like you want to explain more, or like before we jump to the next section? Okay, that's great. So yeah, if you have questions, you're always welcome to ask me afterwards. Okay, so next I will show you how do we use the LDIC and the DVC code. Also, our lab also have lots of the QDIC and the QDVC, and the TPT code will be covered tomorrow. And also we also have the MATLAB finite element based global DIC and the global DVC method. They're also available online. Okay, so first is I hope to show you this just section by section, and I hope you can download this training materials at thisbox.com. So first I will show you Lds model demo, and then show you Dbc demo. And I put a lot of those helpful links in the same Dropbox. So besides our Lds DVC method, there are also other Encore or DICE. They have lots of the nice GUI you can use. But the good thing is from today's demo, I hope you can know what's the basic algorithm post-processing steps for the DIC. It will also help you when you use the Encore or DICE, for example, if you prefer. Okay, so next I will show you the DIC. I will copy this link again in the chat channel in case someone didn't have this link. Yeah, if you have a question, you can also put in the chat channel. So I want to ask for everyone. So do you just want we do everything at the same time? Like I do one section, you also do one section, or do you prefer I just do everything once and then you just watch it and then you try them afterwards? Or I will, maybe I can send up a poll.
Well, I think we may not have time to then follow your steps just afterward.
That's cool. So I can show you one time, right? And then if I will stay an additional 30 minutes. So if you want to try or some ask question, that's okay, right? Is that okay for everyone? Okay, so okay, I will show you just the first one, and then if you can try, I will stay additional 30 minutes, right? So maybe some people they have to leave. Okay, so once you download all the in the training, can everyone still see my screen? Let's double check.
Yes, we can see it.
Thank you, Jean. So in the box, so there are the training DIC DVC materials, right? So there are the codes, reference papers, manuals, and the demo data sets. So TPT materials will be added tomorrow. So you can download the codes and the demo data sets here. So today I will show you DIC and the DVC. Other links are included in this links TXT file. So if you download these codes and download the demo sets, and you can just unzip the code into one of those folders. So for example, here is one of those my LDIC folder. So everything is here. So there's also the code menu there. You can check. Also online on the MATLAB file exchange, we also have the video for the guide and for the algorithm introduction. There's very detailed menu there. The quick demo is you can just click this min aldlc.m file, and you can just, because this MATLAB, you can just run them section by section. So for example, if you run the first section, it's to help you to set up all the environment, add all the subfolders. Also, because we want to achieve the subpixel accuracy, so here we use the bicubic interpolation. So we want to use this max file to do the interpolation stuff. It's much faster than the MATLAB default interpolation scheme. So you need to build the max file here. This max is quite general for lots of the application where you want to use the C++ or C codes in MATLAB. So after you set up this successfully, you will see a message showing here. Even though there's some warning message, but as long as you see the max completely successfully, that usually works. So one thing I didn't maybe I should say clearly yesterday is for the Mac, usually your Macs should already work. Just for the Windows, sometimes you need some additional operation that I put in the email. Okay, once you set up section 1, so you can see lots of those subfolder, they are already added to the path. If it's not, because that's I use the function called add path. If it's not, you can always choose the click the folder to add or remove from the path. But for now, you do, because all this is set up in the automatic manner, so you do need to do that. And the next section 2 is to define your DIC parameter. So also loading your DIC images. One good habit is to put all your images into one same folder. So for example, here you can see I put one of those image sequence in the same folder, or maybe in another folder, but always in the same folder. If you only have 2 frames, you can put in the same path. That's also okay. So here the 2. Jacob have some TIFF data sets that I send Jacob and Jay some additional code, so that will work for your TIFF images. So if I run this section too, so it will ask me to select the image folder, or to use the image names, or you just manually select the image. So you can select the image folder or just manually select images. So here, first I show you, if you manually just you click the 2, and then for example, for the reference image, I click one of those. And then for the deformed one, I click another one. So it will ask, do I want to load more frames? No. So after loading the image, you can define your region of interest. That's the area you want to compute the DIC. Right? So you click one top left point and then bottom right corner point. So I just click it twice. Click one time and then click a second time. So then one of those ROI domain already defined. And the position also shown here on the screen. If you want to assign those values by yourself, you can easily to, you can see in the section, you can always change these values by yourself. And then you need to, as I said, for the local DIC or ALDIC, you need to choose what's the subset size, right? And what's the subset spacing, right? So as we mentioned before, for the subset size, you need to at least have 3 to 8 speckles or features, right? Speckle dots or features. And then for the subset spacing, about 25 or 50% of the subset size, right? So here I choose the subset at 20 and the space at 10. And ALDS is global. You can always choose the recommended one, make difference. And here you can use the parallel tools for the MATLAB. So for my computer, I can use the 4. I can show you more how do you add the preference for your parallel tools. Okay, so for the parallel tools, you can always check on the top of the MATLAB. It's here. It's under the menu of the environment. There's a parallel. You can set up your parallel preferences. If you don't have this, you may not install the parallel tools for your MATLAB. So just Google how to install this from the MATLAB package. And for this setup, you can choose your preferred number of works in a parallel pool. Most computer, this number can from 4 to 20, for example. Usually it's about 4, 8, or 16, or 12. Just choose the number that your computer, based on your computer physical setup. Okay. And then we just run the next section. So this section, so here's what I did. First is I use the FFT cross correlation to compute the initial guess. And then from the initial guess, I compute the ALDS method. ALDS method, we have 2 sub-problems. That's a local problem and a global problem, and then solve everything iteratively. So first step is to use FFT cross correlation to compute the initial guess. You can try the multi-grid search, or try the uniform search, or some manually just search several points. So I would recommend you search the 0 or 1. So if you choose 0, for example, it will use the pyramid image pyramid and track all the definition in the multi-level strategy. The whole field search is just for each of those points. You search a local area for the definition. So where you need to define what's the search, search radius. Oh, it's already solved. I just stopped it first and then section 4. I want to show you what happened. So after section 3, you will solve the initial guess. So this is the solution solved by the initial guess. So this solution is the pure FFT cross correlation results. And so here I choose the method of 0 that's based on a multi-graded search method. So if you don't choose this, you can also choose the like the method 1, that's a whole field search. So for the whole field search, I can use my menu to introduce what's the difference. Again, all this information you can find in the code for the menu. So the searching for each of those subsets, you define a searching area and you search this subset in the deformed image and you find where it is and then find the peak of the cross correlation. So for the previous method, we build a pyramid of those images look like this and search everything in the multi-scale strategy. But if you want to just every point, I don't care about where it is, just search some area and search definition. So that's the previous method 1. So if you choose this method 1, you need to define what's the size or radius for your search zone, right? So if the zone is so small, right, you can see there's no no corresponding subset it deforms to. So that's the bad. So which means you need to further increase your search zone, right? So one of those examples, if your search zone is very small, the solution is very noisy. So you need to further increase those values until you get very nice results. So for example, here, if I first try a 10 pixel for my search zone, right? Because actually my definition is around 60. So you can see it's much more out of the search zone. So you will have very bad results. So bad means the results will look like very oscillating and noisy. It will pump out. You can see it's very bad. This is because your search radius is so small. So then you need to increase the value for your search zone, right? So you just to follow this step. You increase the value for example, for the 50. So this method usually is slower than the method 0 because you see previously method 0 just gave you a very nice result automatically. So now you need to define lots of those search radius. You need to try, but it's always but you know what you're doing, so it's more robust. That's the advantage. So for the 50, you can see it's still small because so you need to further increase those values. So I try 70. This time it should work. Only the first several frames to do this. So after the 6 frames, everything, because we do the image sequence, so previous results will use it to interpret for the following frames. You don't need to do this again after the first several frames. So you can see once your value is larger than the actual definition 60. So it's good, right? So you put the set 5. Further, you can also remove some bad points by setting upper and lower bounds, or if you don't need it, just choose no, or you can directly to clicking some bad points. So if you want to, so for example, if I choose yes, right? So you can use this across bar to click several points, you feel that's the bad points, and then press the enter key. So you can press more if there still are. If you don't need it, just press no. Similarly, you can also clear bad points for the bad white displays bad points. You can click. So if you don't feel there's no bad points anymore, just press enter key. Yeah, my computer is a little bit slow. Also, my list is open. And then after section 3, we jump to the section 4, where we use the ICGM method to solve the deformation. So because we choose the parallel computing, so at the very beginning, it may take several seconds to start this parallel tool. So once it's set up, it only set up once. Once it's set up, you can compute everything very fast. Yeah, here I only use the 4 clusters. So if your computer is much powerful than mine, you will be super fast. So again, you can see this definition looks much better than the FFT results, right? Because just remember in the affine definition, we also include it can handle the larger shear and the rotation and the distortion, right? And again, you can remove bad points again by use the upper lower bounds or something. If the definition is very nice, you don't need to do lots of this menu removal, right? You can just comment these codes for you. Anytime you want to stop the code, you can use the Control-C and then modify based on your personal need. So if I rerun this section 4 again, this is super fast because the parallel tool is already set up. So this part will not be asked you to remove the bad point again. So you can solve the result use the local step. So this is the results use the local method, ICGM method. So this is a classic ICGM local method. You solve the deformation field. Yeah, we're more beyond than the local method because we also have the global step and we do the ADMM iteration. So global step, you just run another section, you solve everything globally, and then you solve everything iteratively in the ADMM manner. So it solves the iteration of the local problem and the global problem. ALDVC have a similar step with this. So after all the solving, you can just save your results in a mat file and plot the results like this probabilities. And if you want to, you can check the ADM convergence on the section 7. For your research, you don't need to do this step. And then you can also compute the strength field use the section 8 and the stress field use the section 9. So I will show you for the section 8. You just run this section. So it will ask you what's the pixel unit, like how many micrometer per pixel or how many micrometer per pixel. So for this example, I just put 1. And you can further smooth deformation field. If your deformation is already nice, you can smooth and more. And also we just code a lot of those methods. You can compute strain. You can find a difference, plane fitting, or find an element. So here I just use the recommended. For the strain, you can use the small strain or Euler strain, large strain, finite strain, or code by yourself. Yeah, use the small strain. You can put your result overlaid with your images, right? You can put in a reference image or deformed image. Here you deformed one. Also for the output format, you can use JPG or PDF. Here you use JPG. And for the overlay image, you can choose some transparency. Here you use 0.5. Yeah, so this output result. You can see the solved results is overlaid with the original images. And then it will be saved. Oh, for this save, you can just because it's MATLAB, right? Once you have these figures, you can save what you want. Also because all this solution is stored here. All the solution is stored starting with the variable name starting with called result. So if you check it here in the variable workspace, so the results have the result displacement for, because here we only have 2 frames, so we only have 1 result. If we have 100 frames, because all the 99 frames is compared with the first one, so you have 99 cells, 99 those in the row numbers. So and solve the definition gradient is solved here. That's the F, and solve the mesh for each frames, and also the string fields, they are solved. So it can be quite useful for your future research. Again, all these saved results here. I saved lots of those. Here I saved here displacement, strength, magnitude, and the formation string. Yeah, you can save into different formats. This MATLAB. Just a quick show you if I want to do an image sequence. So here I will show you if I have the lots of those images like here, right? So I can just run again from the very beginning. I can choose the image folder. Yeah, feel free to leave. You have other things to do. I choose the folder, so all the image will be loaded, and you can define the ROI again, and you can choose the similar to the subset size, subset spacing, and choose all this method. You can. Yeah, so the thing that you can always save everything to deal with the image sequence. Because this is an image sequence, so this definition is quite small for the first 2 frames. Yeah, sometimes you can see there are lots of the image window pop out, right? So you don't need them. You can always find where they are. How to find them where when they pop out, just press the Ctrl+C and then comment those plot functions. All the functions always starting called some plot. For example, here it's also starting with some plot. You can always comment this if you don't need them. Yeah, because this open source code, so you can just feel free to modify based on your own needs. Yeah, I will stop here because this has 39 frames to go. So is there some question for this DIC code?
I just have a question. Is this a cumulative or stepwise DIC?
So this is cumulative.
So you compare the current with the first image.
Yeah, always. So for here, I show you always the first image.
Okay.
Yeah.
Will there be a problem if you have large deformation?
It at least it can handle over 40 or 50 or it can handle very large deformations. Yeah, and also if the definition is super large, I coded the incremental method at 2, but the accuracy is really doubtful. Depends. The most important reason is because for very large deformation, some region they will out of the view. So you need to do lots of explanation. That's usually the accuracy is quite low. oh, you can try, because here you can choose to try the incremental mode here.
Increment, yeah, okay.
You can
That's
try,
good.
but
Yeah,
based on my personal experience, is even the cumulative mode, even the cumulative mode, this code already work well, still work well over 40% strength.
Okay.
If the deformation is super large, many region will, many specimen area will out of the view. If you could already compare the first image, so it's also because it's because nothing to compare, so it's also not meaningful to compare them. Yeah, so the accuracy is low because you rely on lots of the extrapolation. Extrapolation always has the less accuracy compared to the interpolation.
Right.
Yeah.
And also, if we have large deformation, your regional interest might not be able to cover from the beginning. So I mean,
yeah, that's
is
true.
there a way to adapt it?
Yes. Yes. So
okay,
if you do compression, I showed one of those foam compression, it still works for a while. But for the tension, yeah, that's what the problem. Also, this is one of those biggest difference compared with the DIC and the PIV. The DIC, because in the solids, we care about the strain or displacement, right? So we are always in certain of those cumulative mode, right? But for the PIV, you more care about the velocity or vorticity. So you always just compare two frames.
Right.
Yeah, so the one of those difference. So actually, DIC is more challenging than PIV in some way, because the PIV you always compare two neighboring frames. Because the DIC, all the much later frames still compare with the first frame.
Right.
Yeah.
Okay.
So because the time limit, I will just quick jump to the DVC code, and then I will stay here if questions feel free to ask. So for the DVC, similarly, you download the code, there's a DVC package there. You put some example, for example, for the demo data set for the volume strategy here into one folder called DIC image or some other folders. If you open the main LDVCM, just to define the file name and the file folder here. Use the name by the DBC images. And then just run this code, you can get the volumetric definitions. Yeah, I can show you, but before I say this, I will show you how, because in the experiments, you don't have the mat file, right? What you actually recorded in the teeth or these stacks, right? So you need to have some code to change from the teeth or this stack files to those mat file and then run this LDVC code. So in the DVC images, if you look at the, it's called the generated volume mat file. So here I just code a code where you can change those teeth to a mat file. So you put all your teeth frames here into one folder. Based on your need, change some of those names, and then you can just generate this mat file. With this mat file, you can then run this LDVC code. And all the steps the similar as before is just run very beginning to show you. One thing to pay attention is because the volumetric images are much larger than the 2D images, right? So sometimes when you choose the parallel computing, you need to pay attention to your RAM size. Sometimes the parallel computing may not work anymore, so you need to use the single cluster computing. Okay, so for the DVC, same. You can define the DVC region of interest, right? So you can just choose the whole volumetric as your image, or you can just choose a certain region. So if you choose the not open, you just choose the entire volumetric image as your region of interest. But if you choose the open, you can just define it's called a cube or rectangular those shape. So you can define a X and a Y, and you can also define a Z for those cubes. You can always define out of the boundary. Out of boundary, it will shrink back to the closest corner point. So here I define a region of interest, and I can choose the subset size. So here I use the 10 and the spacing. So all this definition is the same as the PPT I showed you before. Oh, so again, here, same, you can use the zero normalized cross correlation or like a multi-grid method. So here to choose multi-grid method, much faster. Also find a difference, how many parallel to open. This computer, the RAM, the low at the 1. You can try 4 or 5. You can try, because I don't know your computer RAM. Yes, just for safety, I choose 1. Yeah, DVC usually is much more computationally expensive compared to the DIC, right? Because you're dealing with the volumetric images. So everything is just one order higher, one dimensional higher. Yeah, it's computing. We need some waiting time. Yeah, but all the steps the same as before. Oh, so again, here the DVC code also have the code menu. You can check. Yeah, you can also feel free to follow my file exchange page or our GitHub in the Frank Lab. So if we have updates, and then you will know what we made. Yeah, so DVC is similar with the DIC, but you to choose some volumetric images. Yeah, again, here is the same. You use some image pyramid multi-scan method to choose the definitions. Yeah, final solution will look like this.
Cool. So I just have a question about ICGN and
yeah, go ahead, Alex.
Hi, Jane. I kind of know so basically for DIC, you use the correlation and you get the Fourier transform and the inverse, right? And then you kind of find the peak of the function, your spline, your interpolation function, right? But that's, for the
that's only the initial guess.
Oh, so that's the initial guess. Okay,
yes.
But yeah, but where did you do the optimizations for the F and U hat, right?
Yeah. So
I know you. Can you just please? I'm not very clear about the algorithm. So can you just briefly explain what is ICGN method?
Yeah. I would like to use this PowerPoint slide to explain.
Okay. Yeah. So what's your object function and what how you actually optimize it?
Yes.
Or is there any function that already being built?
So first, the ICGN. So first, the FFT cross correlation is only the initial guess because it's less accurate to measure the huge definition like this.
Oh, this is a primitive DIC, right? At the early stage, people use this.
Yes, this is only the section 3 for my code. So it's only the initial guess.
Okay. Yeah. Cool.
So after this initial guess, you jump to the section 4, section 5, and section 6, right?
Yeah.
Section 4 and section 5, they are to solving the optimization problem. For example, the minimization, the summation of square the difference. So this is the optimization function.
Okay, so you didn't use the correlation or the Fourier transform.
This is still the correlation, but it's not the cross correlation. It's the SSD correlation.
Okay.
And it's equivalent to the cross correlation.
Okay.
You can try both because actually, if you try this or try cross correlation function, it's the same computational speed. For this iterative method, they are the same computational cost.
Okay.
Because
Yeah,
because
you
what
just minimize over F and U, but
yeah, so I minimize
do
over
it?
F and U, right?
right, but how you actually do the minimization? How you
Oh, so how, because I leave, okay, so yeah. Thanks for the question. So that's why I leave like a homework for you, you know.
okay, yeah, that
Okay.
because you all the paper you said minimize over what and what, and so I don't really clear how you minimize.
Okay.
Yeah.
So C is a correlation function, right?
Right.
C,
Yes.
right? So U and F is the map variables, right?
Right.
Right. So first I can assemble U and F into a long variable called a P, right? So first two is the U, left four is the F, right?
Okay. Yeah. So,
So-
that's a gradient. That's du over
No.
dx. That's a du
No,
dx.
du dx is the F11.
F1. Okay. Okay. Yeah.
Yeah. So P is just so which means C is just a function of the P, right?
Yeah.
Because U and F, they are the first two and the left four of the P.
Right.
So C the function with the P, right?
Mm-hmm.
So Newton-Raphson or inverse Gauss-Newton, the scheme is the gradient Cp delta Pi equals minus gradient C.
Okay.
So first, is this red box clear or not? So this is a general operations iteration.
Oh, okay. Yeah. Yeah. This is a ICGN, right?
Yeah, or Newton-Raphson or ICGN. So that's
Okay,
first
yeah.
For the understanding. This is typical Newton-Raphson, right?
Yeah.
So how this is derived is that you just from the current P naught, current P, you do the Taylor expansion for the capital C, right? To expand until the second term, right? And then you because it's a derivative to zero, so that's why you get the delta P, right? So that's why where we get
Right.
this is general Newton-Raphson, right?
Yeah. Yeah. That's yeah. That's correct. And also negative sign.
Yeah, and because you have the form of the capital C, right?
Right.
Because C is just this. This is C, right? So you have the form of the C. You have the functions how CP look like, right?
Right. Right.
So you can compute what's the gradient C and what's the gradient C, right?
Yeah. Yeah. So you compute gradient over the all the six.
Yes.
Or,
yes.
Okay.
After you compute the gradient C and the gradient C, that's this true form.
Okay.
That's the ICGN.
Yeah. So you basically equal the you have this form and you solve the delta Pi and you can update.
Yes.
Yep.
Exactly. Yes.
Okay.
Yes.
Yeah. So,
Yes.
Yeah. Sounds good.
This is typical Newton-Raphson. So ICGN is just a little bit modified version of this, but the key idea is the same.
Okay.
Yeah.
Cool. Yeah. It's just similar idea, right? Okay.
Yeah, similarly. So section 4, I'm just doing this to solve the P or solve the U and F. That's the section 4, what it did.
Okay.
And
Okay.
yeah, that's a local subset of DIC or DVC we use.
Cool. So your delta, your left right side is a vector for each subset, right?
Yes.
You're right.
So
and the left side is a matrix. So you have to take the inverse, right? Okay.
Yeah, exactly. So because the capital CI is the scalar, capital P is the vector in the length of the 6.
Right. Yeah.
Right.
Yeah,
So
you
gradient
yeah.
C is the vector 6 by 1, and the gradient C is the vector 6 by 6.
Cool. Yeah.
In 3D, it's different. 3D, your capital P will be you have 3 displacement components, and you have 9 components for the F. So that will be 12, right?
Right. Okay.
Yes. But the theory is similar. Oh, okay. Well done. So after that, you can choose to apply some median test. So general cases to apply 2, and then you have the initial guess results. So this is what just Alex you said for the because this is this uniaxial. You see, this FFT solution, and then we apply to the section 4 and the section 5, and then do the ADM iteration. Okay. This is FFT results. And if you want to quantitatively compare all the error or something, I would suggest to read the reference paper where I put because there's a table to quantitatively compare what's the error between these methods. So for example, DVC, right? If you look at the 2020 paper, to compare the local, global, and the AL and the FT, compare these 4 methods. We have the quantitatively measurements, for example, what's the error you measure the translation, unit active stress, and rotation, and to compare these different methods, what's their error. So for example, for FFT, the typical error is about 0.1 voxel. For example, it's on the order of 0.1. But the local ICGN is about 0.07 or 0.0, and the AL is much smaller even than the local. Because you can see this is the local FT is because you always rely on the rigid translation assumption, right?
Right, yeah.
And the ICGA you can also handle the distortion or rotation or shear, right? So it's more accurate. But the local ICGN you ignore the global kinematic compatibility. So which means you only solve each subset independently, but you ignore its connection with its neighbors. By including the information with the neighbors, you can further decrease the accuracy, further increase the accuracy.
Okay.
Yeah.
Okay.
We also combine lots of indentation to other definitions.